Alright, this last part is going to be about calorimetry. If you say it really fast, it sounds like you know what you're talking about. You got two types of calorimeters up at the top. The one on the left is called the bomb calorimeter. This one is called the basic. You can do this at home if you wanted to. This is actually how we get calories in food. We burn it, water boils, or we measure the change in temperature of the water. It tells us the heat, which tells us the amount of calories. So when you're doing these, it's just another MCAT formula. But you tend to have two masses given to you. So this one, if you read it real quick, you see a 0.303 grams of the sample, and you have 240 grams of water. We don't really care about how much the sample has. The only thing we're worried about is the water. Why is that? Because we know the specific heat of water, so it's easy, and everything else we do in the math equation is based around the water. So only pay attention to the water. So it's going to be Q equals MCAT. So our M is going to be the 240 grams of water. Our C is 4.184, because it's water. You got to memorize that one. And then your delta T is going to be your final, which is going to be 27.55 minus initial, 22.53. Do that real quick in your calculator. And you will get 5,041. Here's some more of it. You can read the question for yourself, but calculate the heat released when 1 gram of sample is combusted. Okay? Remember, we don't really care about the gram of the sample. We care about how much water is in there, because that's how much is going to affect the temperature change of the water. So Q equals MCAT. M is going to be the mass of the water, which is going to be 1,200, times the C of the water, 4.184, times the temperature change of the water, which went from the final temperature of 33.2 to from initial temperature of 25. Put that on your calculator, and you get a positive 41170.56 kilojoules. Now that was quick. I trust you can do these in your calculators. And this one, we're not going to do, so don't worry about it. Onward through the phone. So then the next part, the very last part of our notes, you get this big, ugly, nasty equation. Don't worry about it. I'm going to simplify it for you. Don't memorize that. It is on your formula chart, but I don't have time to go through and explain what each one of these little math symbols means. But you got your steps right here. You definitely need to know the steps. And then, more importantly, the procedure. So take a few seconds, pause it, copy those down, and then I'm going to show you how I do these problems. All right, these problems are easy to see because you'll always be given this little chart down here. If you don't have a chart, don't do what I'm about to do. If you have a chart, just immediately go into this mode. You're going to get a lot of these in class because they're easy. They do take a while, but they're not hard. So the first thing you should notice is we always start with the products. So when I do these, I have a product side, and then I draw a little T-chart with the reactants. That way I keep them separate. So then, you multiply the delta HF, that is from the chart, by the coefficient, which is from the equation. So the first product we have is CO2. That coefficient is 3. So I would say 3 times the delta HF of CO2, which is right here, negative 393.5. Then I'm going to put that in parentheses. Then I'm going to add the next one, 4 H2Os. So 4 times the H2 from the chart, negative 241.82. Put those in parentheses, and then you sum the reactants of the products, or you sum the heats of the products. That's going to give you negative 2,147.78. Okay, now let's switch gears. Go to the reactants. C3H8 has a coefficient of 1. You can do the same thing. 1 times negative 104.7. Plus the 5 from the O2. Then you notice the O2 is not on the chart. If it's not on the chart, it's 0. Because elements by themselves aren't going to form anything. They're not going to fuse together with anything. So times 0. That gives you negative 104.7. And the very last part, like we've been doing the whole time, is products minus reactants. So it's negative 2147.78 minus negative 104.7. Put that in your calculator. It should keep it all straight for you. And that will give you negative 2,043.08 kilojoules. That's all there is to it. Let's go ahead and do another one. All right, so we see the chart. So once we see a chart, we automatically do our T-chart. Products, reactants. Then we start with the products. Coefficient of the first element is a 1 times the graph value, negative 226.00. Put that in parentheses. Plus the next one, 12. 12 times O2 is not on the chart. This is going to be a 0, which gives us a nice easy number of 2226.00. Then you move to the reactant side. 12 from the CO2 times the graph value of CO2, negative 393.5. Plus the next one, the 11 from the water, times the graph value from the water, 241.82. Put that in your calculator. Make sure you're using your parentheses. That's going to give you negative 7382.02. Then, like always, it's going to be products minus reactants. So it's going to be negative 2226.00 minus the negative 7382.02. Please don't get lazy with that negative. It will change the value. And that's going to give you 5156.02. That's going to be positive, so that's going to be endothermic. That's all there is to it. I forgot to come back and tell you if this was endothermic or exothermic. That negative value makes it exothermic. There we go.